Unit 1, The Alphabet and Grammar of Geometry. Lesson 1.5, Brain in Hand Problem Solving. This is by far the most critical preview video of the entire year. Quick background. I have an Association of Christian Schools International lifetime certification for teaching, and I have a master's in education from Dominican University. But you need to understand a little bit more of my background, my bachelor's degree, and prior teaching experience. I have a bachelor's degree in occupational therapy, which is a certain type of rehab degree which uses activity for the gaining of independence. So I have a background in understanding neuroanatomy and physiology. That's part of my original bachelor's degree training. So it's important that you understand that I have intimately studied what I am talking to you about right now. If you'd like more details about my background, ask me in class. So we're going to be talking about a process called brain in hand problem solving. Date, time, and location, parent, guardian sign off, focused attention equals faster work. Please, especially this lesson, turn off all distractions. I'm going to paint a little mystery I have for you here and see if you've experienced this. Vocabulary you're going to need for today. A neuron, frontal cortex, digital immigrant, digital native, hypertext skimming, linear reading. A neuron is the smallest cell in your brain. Frontal cortex is the thinking part of your brain. Let me paint a scenario. In the around 2005, 6, 7, I started noticing a shift in my students' approach to geometry. I would write a geometry problem on the board, and I'd be tutoring with a student, and they'd just glance at it, whatever the geometry problem was, is they'd just look at it, and they'd immediately say, almost instantly, within 5 seconds, I don't get it. Notice where the hands are. They didn't pick up a pen, they didn't draw anything, they didn't put their hands on the diagram. They simply glanced at it, and within 5 to 10 seconds max, usually they would just say, I don't get it, and then they would stop. And this became increasingly common. And as a teacher, I started asking myself, why are students not perceiving and understanding visual diagram problems? Why did it seem so hard? And I did my master's thesis in how digital technology is changing the way our brains process information. And it's important that I did my master's thesis because I can see the change, because as old as I am, without any dates, I am a digital immigrant, which means I did not hit digital technology until my college years to any degree, where you, my students, are what are called digital natives. You were practically teething with cell phones in your mouth. So how is that changing the way brains process information? 5 key things discovered in my master's thesis. 5 very important, and I have all of these cited and text if you wish to investigate further. 5 key thoughts. First key thought, your hands and your fingers are connected to your frontal cortex, which is your frontal cortex is the conscious thinking part of your brain. And your hands and how you interact physically with your hands gives input to the thinking part of your brain. The simple truth is, if you don't use your hands, you are not thinking. That is a very simple but very important concept. If you're not gesturing, physically making models with your hands, your brain is not processing physical information. Geometry is a physical, hands-on math. And your hands are connected to your frontal cortex, the thinking part of your brain. Key thought number 2. Because the way we use our hands has changed, the way we're thinking has changed. We keyboard more than we write. We click on stuff more than we color physically. We tap on screens more than we actually touch physical things in reality. And because we're doing more of this and less of this, it is changing the neurology in our brain, the way we process information. And for the most part, a more negative way. We're less rich and deeper in our thinking because we're spending more time in the abstract world of digital technology rather in the physical, real world where physically writing with a pen or pencil on paper, especially in cursive, creates more neural connections than tapping on a keyboard. Physically coloring with multiple colors on piece of paper or doing clay work uses more neurology than clicking on stuff. And making physical models of science experiments, physical models of other items, 3Ds, things you can get your hands on, gives you more of a context than simply tapping on screens. Digital technology is changing the way your brain processes information, and for the most part, it's not for the better. Key thought number 3, screen reading is different than print reading. These books I'm citing right here, the iBrain, again, these are my footnotes, if you will. Screen reading is different. It's very important. When your eyeballs hit a screen, even this screen that you're watching, we have a tendency just to kind of wander and skim. But when we're looking at a book or a piece of paper, we tend to read linear, line by line, and catch much more detail. That's why I am also encouraging finger on the line. Because in math problems, if you skip a single word, your eyeball just skims right by it. There goes the whole math problem. The very simple word is, if you skip over that, that's an equal sign, folks. And if you skip over a single word when you're reading, your brain is not comprehending. Key thought number 3, increased finger usage and usage of your hands and gestures and fingers on paper, on physical things like paper and models, increases brain function. Again, Todd Oppenheimer, I have all my citations below. And here's the most important concept. There is actually a place in your brain that processes visual mathematical information. Okay, I already introduced you. Physically tracing and drawing math diagrams increases comprehension. This is from Neuropsychologica, the actual article's down below. So this frontal part of your brain, the frontal cortex, is the thinking part of your brain, your conscious thinking part of your brain. Now, there's other parts of your brain that unconsciously processes information. And of course, you have your visual cortex, where your eyeballs are out here. Forgive me, artists. And your eyeballs send signals to the visual cortex, and the visual cortex sends images to the thinking part of your brain. But it's very important that you do not perceive all your vital information through your eyeballs. There's another part of your brain that helps you process visual spatial problems related to math, and it is specifically called the left angular gyrus. It's just behind your left ear, a little deep, the left angular gyrus. And that part of your brain processes visual mathematical information, is specifically connected to what are called the eye fingers, and that is your your first finger, not counting your thumb, and your middle finger, your index and your middle finger. Those are called your eye fingers. Those are specifically connected. They have nerve endings that go all the way and feed information to that left angular gyrus to process our understanding of math, and then that feeds it to your thinking part of your brain. This is called finger gnosis. Finger gnosis. Gnosis means to know. So when you are not using your hands to trace diagrams, draw diagrams, circle stuff, underline stuff, filter stuff, make models, when you're not using your hands, you're not processing mathematical relationships and geometry. Now, what does that look like for the class? Let me give you some very simplistic examples. Activating the left angular gyrus. You do not activate that part of your brain through your eyeballs. You activate it through your fingers. In each of the problems, slowly trace and label the given information. Find the unknown. If you have your quad pen, let's get that out. In segment FD, the distance F to E, I'd like you to bracket F, E. Trace that 6. Cross it out. And F to D is 18. Bracket F to D, 18. You're going to find D to E. I like you to bracket D to E. Unknown. One more time, I'd like you to trace F to E, 6, F to D, 18, E to D. You have 10 seconds. If at some point you went, oh, it's 12, as you trace, that fed the information physically 18, 6 underlines it, you subtract, and that is 12. I want you to physically trace all of these very slowly. Let's try another one together. In the segment GD, the distance F to D is 15. So ready? I'd like you to bracket F, I'm using blue, to D, 15. F to E is, that should read 12. Should read 12. F to E is 12. G to E, from here to here, is 18. Your goal is to find G all the way to D. Take 30 seconds. Find that whole line. What you should have noticed that if this from here to here is 12 and here to here is 15, E to D must therefore be 3. Once again, if from here to here is 12, notice I'm still physically tracing. And from here to here is 18. Then this is 18 minus the 12 is 6. And then I went G all the way to D. So I physically trace. That's going to be 6 plus 12 plus 3. $21. You are physically tracing every single one of these segments. Now we're going to work with something called angles. Trace and sweep the given information. Trace angle B, find angle B. We're just going to physically trace this diagram, every aspect of it. So first, I just like you to trace that line. Just physically trace it. Like you to trace that ray and that ray. Now I'd like you to physically trace a rainbow on the line. Trace a rainbow on the line. Switch colors if you can. Trace the 115. Squiggle angle B. Find angle B. Twenty seconds. At some point in your tracing, if you trace this rainbow a second time, if you don't get it the first time, feel free to trace a second time. That should have registered in your brain, oh, wait a minute, that's half a circle. That's 180 degrees. A full circle being a 360. That's 180, and from here to here is 115. I simply go I get 65 degrees. Trace and sweep the given information, find angle B. First, I'd like, in using blue, I'd like you to sweep 78. Using green, I'd like you to sweep 240. Using red, I'd like you to sweep angle B. Switch to black. Do this. Physically trace all the way around. Most of you, the minute you did this, it was like, oh, wait a minute, that's 360 degrees. That little instantaneous reaction of perceiving 360 as you physically trace, that is the left angular gyrus being activated, folks. So you can see that you're simply going to add 78 plus 204 and to get angle B, we simply take that away from 360. 78 degrees. So once again, the tracing of segments, the sweeping of angles, that physical activity of your pencil interacting with the diagram is what activates the left angular gyrus. Just staring at it with your eyeballs does not do this. We're going to use this even when we're doing algebra. We're going to trace and sweep and set up a thing equation, then an algebra equation. Use that to solve for x. Very important. Using red, I'd like you to trace the straight line, sweep the straight line in a rainbow, mark your 180. Using blue, I'd like you to trace and sweep that left angle. Using green, I'd like you to trace and sweep that right angle. Geometry is not about the numbers. It's about the physical things of angles and planes and triangles and hexagons and cones and spheres. So you're going to learn to do a thing before algebra. This is what I mean by a thing equation. In this diagram, using the blue angle plus the green angle equals the larger red angle. Notice that's a thing equation. I'm talking about things before I talk about numbers. Then we're going to circle, plug, chug. Circle, plug, chug. Chug just means do the problem. Watch. Circle the blue. Circle the blue equation. Plug it in. Circle the green. Circle the green equation. Plug it in. Circle the red. The red sweep is 180. Plug it in. Circle, plug, chug. Now you will solve for x. Now, if this was algebra class, you're like, woohoo, I found x, I'm done. No, but this is not algebra class, friends. This is geometry. So 99.9% of the time, you are not just solving for a variable. I'd like you to take that variable and you're going to plug it in right there where it belongs. So 3 times 20 is 60, plus 19, that's 79. 5 times 20 is 100, plus 1, 101. Here's your check. 101, 79. Oh, ta-da, it's 180. Students, on a test, if I were to give this problem to you, I want to see things before algebra, and then I always want to see a check. Once again, let's try this things before algebra here. Using blue, please. Sweep. Switch to green. Sweep. Switch to red. Sweep. Switch to black. Go all the way around. Here's your thing equation. Things before algebra. We know that the red angle plus the green angle plus the blue angle is going to equal a circle, which is 360. There's your thing equation. Now, circle, plug, chug. We circle the red angle. We physically circle the algebra. Circle the green. Circle the green angle. Notice that's a minus sign there, so we're going to take this and change that to minus 48. The blue. Go ahead and solve for x. Things before algebra, circle, plug, chug. Now we're going to go ahead and we're going to plug this in. So I have 74 minus 36. So in the margin, 74 minus 36. No, I don't want you using a calculator there for two-digit subtraction. Welcome to third grade math. So if we put a 74 there, you're going to end up with 38 degrees. I put a 74 here, technically minus 48. This becomes 26 degrees. And then your check is 296 plus 38 plus 26. $360 check. So it's very important when we're working with complex problems, more complex problems, aka real life problems, also known as word problems, and very often you want to do not allow your initial reaction, I don't get it, to sabotage your effort. Most of you think you have to understand first and then you apply effort. That is not true. You don't understand first and then apply effort. That's why many of you, when you hit that I don't get it in about 10 seconds, you stop because you think, oh, I have to understand the problem before I do any effort. That's not the way the brain works. The brain works like this. Effort brings understanding. Effort brings understanding. Your brain is activated by effort. Simple example. You and your friends are talking and someone mentions a a piece of a song and you in your brain you're like, "Oh, what's that song called?" Okay? And you can't remember it, but you spend about 30 seconds trying to remember the song, effort. 3, 4 hours later, in the middle of history class, boom, your brain serves up to you, aha, here's the title of the song. Same thing happens with names of movie stars you recognize, and you spend about 30, 45 seconds, maybe even a minute, racking your brain. Oh, what's that movie star's name? Or what's the name of that book? And you try to remember, and you actually put forth effort in your brain, and then you stop and you think your brain's not thinking, but that's not true because you put forth focused effort to try to remember. Your brain unconsciously started hunting for that information so that even hours later, bam, here comes that movie star's name, the title of the book, the name of the song. So effort yields understanding. You don't understand first and then apply effort. You apply effort and then you get understanding. But the question I get most often is if I don't know what to do, what do I do? So I give you 5 simple things what you can do when you don't know what to do. All of this translates into effort. And as you invest in effort, your understanding will increase. This is called brain in hand problem solving techniques. 5 things you can do when you don't know what to do. First, and by far the most important, always read with 3 body parts 3 times. The 3 body parts you read one time through, finger on the paper, lips moving, eyes on text. That's your 3 body parts. 3 times, that's your first time reading. Second time reading, you go back, you filter or highlight or underline keywords, numbers, watch out for units. Third time reading, draw, label, list, cross out. Draw, label, list, cross out. Draw, label, list, cross out. Physically trace all diagrams and label all diagrams. No naked diagrams. All your diagrams should be physically drawn, physically retraced, labeled. That's what I call dressed up. No naked diagrams. Number 1, read with 3 body parts 3 times. Number 2, the 5 R's. Review your reference folder, recite recent revelations. Review your reference folder, recite recent revelations. Review your reference folder, recite recent revelations. If you don't know what to do, flip back into your reference booklet and verbally recite what are some things you've recently learned. You can always open your reference booklet. Do not treat your teacher or your classmates like Siri when you can flip through your own reference booklet. Physically flipping through the reference booklet implies effort and it increases understanding. Super important. Do not ask yourself, what should you do to solve the problem? Stop asking the word should. Ask yourself, what can I do? whether or not it solves the problem, just ask yourself, what are some things I can do? I'll demonstrate what that is. Squeeze the sponge means I want you to take the problem and squeeze out all the information possible, just like you're wringing out a kitchen sponge. You don't hunt for one or two simple things. I want you to find all possible stuff. Squeeze out all possible information out of a diagram or a word problem. 4, when you're working with equations, equations have two sides with an equal sign. Equations have two sides with an equal sign. When you write equations, you write them with two sides and an equal sign. For example, if I asked for the slope equation, most of you would write this, y2 minus y1 over x2 minus x1. Wrong. That is not a slope equation. An equation has two sides with an equal sign. So if I asked for the slope equation, it would be this. Slope equals y2 minus y1 over x2 minus x1. Equations have two sides with an equal sign. When you're working with equations, learn to what I call circle, plug, chug. Circle items, plug them in. Chug is my euphemism for do the work. 5 things you can do when you don't know what to do. You can always do these 5 things, even if you have no clue how to solve a problem, because effort brings understanding. Let's recap a couple things before we do an application of this. If I want to find the perimeter of a rectangle, perimeter, I'd like you to physically walk it around, put a little arrow there. Trace the perimeter. Perimeter, think picket fence. Picket fence. You have 2 lengths, 2 widths. So perimeter, you walk it around. That's going to be length plus width, length plus width. Some of you shorten, and you get this. Perimeter equals 2 lengths plus 2 widths. Both of these are perfectly acceptable. I personally prefer this one because very often with this one, students drop that plus sign and they just multiply everything, which is incorrect for perimeter. So perimeter, think picket fence. Area, I want you to think grass. I'd like you to physically shade the area. And for rectangle, area equals length times width. We're going to use these in the next couple problems. We are going to model reading with 3 body parts 3 times. Ready? Put your finger right there. Read out loud with me. Finger, not pencil. Finger. The perimeter of a rectangle PQRS is 26 degrees. The longer side PQ is 3 centimeters longer than QR. Find the area of the rectangle. That's pass number 1. Pass number 2, read with 3 body parts 3 times. Here's our second time. We highlight our key information. We're dealing with perimeter. Is an equal sign. 26 centimeters. The longer side, 3 centimeters longer than QR. The longer side PQ, longer than QR. Find the area. So area is what we're finding. Let's write down our area equation, length times width. Now, pass number 3, draw, label, list, cross out. Draw, label, list, cross out. So we already know the longer side is PQ, so I go like this. PQ is the longer side, R, shorter side, S. I have accounted for this. Now, physically trace PQRS. Physically trace PQRS. Put a little arrow there. I'd like you to write this down. Perimeter is 26 centimeters. Counted for this. We have length and we have width. Length is usually the longer and width is the shorter. Length, the longer side is, that's an equal sign, 3 centimeters longer than QR, which is the width. So the length is 3 centimeters longer than, that's a plus, not a times, longer than QR, which is our width. So length equals 3 plus the width. Find the area. Draw, label, list, cross out. Okay. Our goal is to find the area. So you don't ask yourself, what should I do to find the area? That's not your first question. You're not over here asking, what should I do? You ask yourself, well, what can I do with the given information? We're not starting with area because we don't have the length or the width. What do we have? We only really have one number here, and that's the perimeter. So that's where we're going to start. So can you easily write the perimeter equation? I'm going to write that down. I can write that down. That's easy enough. Why did I start with that? Because I'm given the perimeter. Let's see what else we can do. Let's try circle plugging chugging. How about we circle that P? What could we plug in? Circle that P. Wait a minute. Circle the 26, plug it in. I could replace that perimeter with a 26. Let's see what else I can do. Circle that length. I can replace length with 3 plus W. Plus, bringing that W down, plus my length here is 3 plus W. I'm going to cross it out as I account for it, plus W. Looky there, we are down to one variable, folks. Let's collect like terms. Solve. Woohoo, you solve for something. Never stop with a single variable. Always keep in mind what we're trying to find. We're trying to find the area, which requires the length and the width. Right now, we just found the width, so we're going to draw an arrow, plug it in there. I'm going to put a 5 there. Now I know my length. I'd like you to circle the length. My length Come up here is 3 plus 5, so my length is 8. Now I can finish my area. 8 times 5, that's 40. I check for units. My original units was centimeters for perimeter, so area is going to be centimeters squared because it's the second dimension. So the area of that rectangle is centimeters squared. Let's try another one together. The area of PQRS is 48 centimeters squared. The longer side PQ is 3 times the length of QR. Find the perimeter of the rectangle. Read with 3 body parts 3 times. Now we are going to highlight keywords. We have area is 48. That's an equal sign. The longer side is 3 times the length of QR. Find the perimeter. So let's write down what we know. Longer side is PQ. That means R and S goes this way. Whenever you're dealing with area, I always want you to shade the area. So just shade this, physically shade it. Underneath, we're going to write area is 48 centimeters squared. The longer side is 3 times the length of QR. So if QR is our width 3 times, this is going to be 3W. Our goal is to find ultimately the perimeter, which is walking around like that. We don't start with what we're looking for. We simply ask, what can we do? Well, I have the area, so I could easily write down the area equation. You can always do that. You can always write down equations, even if you don't know what you're doing. So we wrote down our equations. Let's see what we can do with this. Well, I have area. I know what the area is, so I'm going to circle that and plug it in. I'd like you to circle length and ask yourself, what do you know about the length? Oh, I can replace the length with 3W. Let's do that. Then here I have the W. Lo and behold, I am down to one variable. Super important, folks. W times W is W squared. We're going to solve by dividing by 3. The opposite of squaring is not dividing by 2, it's square rooting. The opposite of squaring is square rooting. I just found my width. So if my width is 4, my length is 3 times my width, so that's 12. Now you can walk around your perimeter. 12 plus 4, 16. 12 plus 4, 16 again. My perimeter equals 32. My area was centimeters squared. Perimeter is just centimeters. And we are done. I know this is a little bit longer today. It was very important to get through the basics. If you need to, pause this video and take a 5-minute break. We have about 7 minutes left here. So if you need a break right now, take a 5-minute break, pause the video, and come back. Now we're going to apply brain and hand techniques to a real-life scenario. Number 1, we read with 3 body parts 3 times. Put your finger physically right there. And I'd like you to read this out loud. Mr. and Mrs. Tumnus wanted to fashion a concrete, rectangular patio in their backyard. The width of the patio is 3 feet shorter than the length. The perimeter is 54 feet. It takes 10 60-pound concrete bags per square yard of patio. Each bag of concrete costs $3. Calculate the cost of the concrete for the patio without tax. That was finger track read out loud. Now we're going to highlight and underline keywords. They wanted a rectangular patio. The width is 3 feet shorter than the length. Very important. That is an equal sign. So let's write it like this. The width is 3 feet shorter than the length. So the length minus 3 feet is the width. The perimeter is 54 feet. So we're going to go like this. Perimeter is 54 feet. It takes 10 60-pound concrete bags per square yard of patio. Each bag costs $3. Calculate the cost of the concrete for the patio. Now, concrete, I'd like you to shade, please. Shade the rectangle. Concrete shaded, that's where the concrete is. You should feel that concrete is an area concept. So underneath, let's write the area equation. Area equals now, as we account, draw, label, list, cross out. Let's label our diagram. Width, length. The width is 3 feet shorter than the length. So the width is whatever the length is minus 3 feet. The perimeter, put a dot there, walk it all the way around, trace, a little arrow to represent going around. Perimeter equals 54 feet. I have accounted for this information and this information and this information. For a square yard of patio, so for every 1 yard squared of patio for the depth we want, it takes 10 bags of 60-pound concrete, and they cost $3 each. I've accounted for this information. Our ultimate goal is cost. I always like to box what the ultimate goal is with a question mark. Now, you do not ask yourself, what should I do to figure this problem out? The minute you say should, your brain stops. You ask yourself, what can I do? And asking that question, you start with what you have. We don't have the area, although we need it, but we have been given the perimeter. Let's write that down. And we know that perimeter equals 2 lengths plus 2 widths. Knowing that, let's see what we can plug in. Circle the 54. I could put the 54 where the perimeter is. I have 2 lengths and 2. Now I don't want a W there because then I have 2 variables, but I can replace that W with length minus 3. So circle, circle, draw an arrow, plug it in, parentheses, length minus 3. Now I'm down to 1 variable. Solve. My length is 15 feet. So my length is 15 feet. That means my width is minus 3 is 12. Now we can start working on the concrete because now we can find the area. Our area equals length 15 times width 12. And we get 180. So our area is 180 feet squared. Now the concrete comes per square yard, and our area is in square feet. So we need to get square feet into square yards. Be very, very careful here. Most of you think feet and yards is a 1-to-3 conversion rate. It is not. Take a look down here. When you change dimensions, you change ratios. When you change dimensions, you change ratios. Area is in the second dimension. So a square yard is 3 feet by 3 feet. So 1 yard squared actually is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 yard squared is actually 9 feet squared. So to get this into yards square, we're going to divide by 9 feet squared. Now my units are the same. So 9 goes into 18 twice. We're going to add that 0. So my area of the patio in square yards is 20 yards squared. And my storyline For every square yard, I need 10 bags, and 10 bags at $33 each. So I need $30 for every square yard. So if I have 20 square yards times $30, because it's 10 bags, my cost for the patio, $600. Students, I want you to try this one on your own. I'm not going to give you the answer this time. So you're going to do this one on your own, following the techniques I just taught you. We will go over this last page in class. I will not give you the answers online. Finish this on your own in pencil. Show all your work.